So when you're ready, please introduce yourselves, and then you can begin, and I'll start your timer.
Good morning, judges and audience. My name is Tianle Liang.
My name is Prabjay Chandran.
My name is Truman Graves.
Are we ready? Yeah, good to go. All right, thank you. Good morning, judges and audience. Today, we are excited to present our take on the hot button issue, staying cool as the world heats up. I'm Tianle.
I'm Prabjay Chandran.
I'm Truman, and we're from Zionsville High School. Our research focused on how Memphis, Tennessee can best prepare for extreme heat events. In question 1, we used Newton's law of cooling to model the temperature in non-air-conditioned homes over a 24-hour heat wave period. We saw that apartments were 1.45 times as affected as single-family homes. In question 2, we projected peak grid demand over the summer months for the next 20 years. Our model saw a 20% increase by 2044, meaning that Memphis will need to upgrade its power grid to better prepare. In question 3, we created vulnerability scores for all 27 Memphis neighborhoods, which can be used to adequately address policy issues. We hope that our models will prove indispensable to Memphis policymakers as they seek to protect their communities for years to come.
We'll begin with the first 3 challenges facing the city of Memphis: speedy transfer of heat into non-air-conditioned homes. To analyze this, we've developed a model predicting the changes in indoor temperature of a non-air-conditioned dwelling over a 24-hour heat wave period. We chose Newton's law of cooling as the core of our model for 2 important reasons. First, it directly reflects the physical reality of heat flow, tracking how indoor temperatures of a non-air-conditioned home change based on outdoor ambient temperature changes. The second most important reason is that it's a simple yet very powerful model. It directly reflects things like HVAC, building engineering, and also ASHRAE standards, so we can adapt our parameters based on that. Like I said, we didn't just stop at the basic Newtonian model. We adapted it based on parameters from ASHRAE standards. We added a solar heat gain quotient, A. This reflects things like windows causing heat to be transferred inside the building. We also added a constant internal heat gain quotient, Q. This represents things like people and appliances within the home that generate heat. Overall, these 2 made our model more realistic without making it too complex to solve. By taking it from the ASHRAE standards, we can map this out for both apartments and single-family homes, the 2 most common home types in the Memphis area. Our values K, A, and Q are as shown for both single-family homes and apartments. As you can see, the respective values for K, A, and Q for apartments are higher than the respective values for single-family homes. This is due to show that apartments transfer heat inside significantly faster than do single-family homes. This is due to 3 key reasons. First, apartments have worse insulation. They have more cost-effective materials and thinner walls, meaning heat transfers inside significantly faster. Second is solar heat. Apartments have more windows, especially in multi-story buildings when this becomes a bigger issue as solar heat transfers inside significantly faster. Third is occupancy density. Apartments often house more people in a smaller amount of space, leading to a higher Q value as shown.
Here you can see our model graph for the given data from M3. As we can see, apartments are much more volatile to heat transfer than single-family homes, which we also see reflected in the respective maximums. Specifically, apartments are 1.45 times as affected by ambient or outside temperature, 1.6 times as affected by solar heat gain from the sun, and 1.25 times as affected by internal heat generation, showing they are overall much more volatile to heat transfer. Now onto our sensitivity analysis. We shocked both of our ambient temperatures by 2 degrees Celsius, and you can see the corresponding shifts on the graphs here. Our apartment model shifted by 1.98 degrees Celsius, and our single-family model shifted by 1.9 degrees Celsius. We can see that this means that apartments are more vulnerable to changes in temperature due to lowered insulation standards compared to single-family homes.
Let's move on to question 2. During summer months, AC and household appliance usage spikes, putting a strain on the Memphis grid called peak demand. In question 2, power hungry, we are tasked with modeling this peak demand for the next 20 years. Before even modeling, we first had to create a reliable data pipeline to extract Memphis demand. We used open data from the U.S. Energy Information Administration for the whole U.S. region, extracting monthly peak demand and then factoring in annual customer counts to create this metric, monthly demand per customer. And then, from M3's provided data, we calculated a 1.4 times ratio between Memphis and US demand, and thus calculated the peak summer monthly demand per customer in Memphis from 2001 to 2024. We also had to prepare our explanatory variable. heat wave temperatures. We saw a very special pattern in this, namely the sinusoidal and the cyclical pattern in temperatures. So we decided to extend our explanatory variable with SARIMA, a time series that specifically targets seasonality. We optimized hyperparameters through AIC scores testing 1,080 combinations of hyperparameters, reaching the seasonality constant S of equal to 5 years. In our results, we see these clear 5-year cycles, which actually makes sense because of climate patterns called El Niño and La Niña, which are weather phenomena that occur because of ocean winds. We projected a 70% confidence interval, which you can see shown in red here, and the graph shows both historical data and projected data. We see in the next 20 years, the average heat wave peak temperature will reach 38.96 degrees Celsius, up 1.5 degrees from the last 20 years. Now that we have both the explanatory, heat wave temperatures, and the response, peak demand per customer, we were able to move on to our main model, gradient boosting with XGBoost. We chose gradient boosting because of its historical relevance in climate modeling and the robustness to overfitting. We optimized hyperparameters using mean absolute error, MAE, reaching around 80 kilowatt hours. In the next 20 years, we see a 1.45% increase in peak demand per customer with a 1.77% increase per 1 degree Celsius increase. In this final slide, we show the peak demand we projected for the entire Memphis grid. We started off with projecting peak demand per customer, and now we multiply the actual customers in the Memphis grid around 431,000 in 2024 and factored in a 0.6% population growth rate. In 2044, we see around a 1.76 billion kilowatt hour projection for the peak demand, which is up 20.2% from 2024, putting a drastic strain on the electric grid if there are no large infrastructure renovations. Now on to question 3.
Our final question combines math modeling and urban policy. We're tasked with developing vulnerability scores from heat waves for 27 neighborhoods across the Memphis area to help policymakers allocate resources more equitably.
We started off with 22 neighborhood variables, which is too much to analyze. So we don't have a label, right? So we had to make our own vulnerability metric. We first started off with an unsupervised learning technique called principal component analysis, PCA, projecting the original 22 variables into an orthogonal feature space, creating 4 principal components called PCs. This was very effective, not only simplifying the problem, but also preserving nearly 85% of the original variance. If you can see on the board here, PC1 represents the highest explained variance ratio called EVR, PC2 represents the second highest, etc., etc. On this slide, we can see the PC results with their respective EVRs. We can see that PCA was not only very effective, but also very interpretable. If you look at PC1, you see that the top variables by loading factor are households with 1+ vehicles, population age 16+ working, and the primary work transportation is driving. We see that these 3 variables all represent their sector workforce mobility very well. Similarly, PC2 represents aging urban density, PC3 represents housing diversity, and PC4 represents development and income. Our PC results that we got were not just random, but actually represent real-world socioeconomic sectors. We summed each of the PCs, weighted by the respective EVRs to get our final goal, the vulnerability index. And we chose positive or negative contributions based on their specific relationships with vulnerability. For example, PC1, workforce mobility, is negated because workforce mobility, when it goes up, vulnerability naturally goes down. This is similarly shown in PC4, development and income. However, in PC2 and PC3, aging urban density and housing diversity, they remain positive because they have direct relationships with vulnerability. Our equation is shown below.
Here you can see our vulnerability scores graphed on a map of Memphis, Tennessee, with higher vulnerability scores in a deeper red and lower vulnerability scores in a deeper green. As we can see, PCA is very easily interpretable. The most vulnerable neighborhoods are concentrated on the western side of Memphis, where there's higher urban density and poorer communities. That's also where downtown is. On the other hand, the least vulnerable neighborhoods, such as Collierville, are concentrated in the wealthy outer suburbs. You can see here our top 3 least and most vulnerable neighborhoods. We hope that policymakers will pay key attention to geospatial risk distribution in order to ensure an equitable use of resources.
For our sensitivity analysis, we analyzed how changing the weights of our principal components impacts our vulnerability scores. We began by shocking the EVRs, essentially the weights of each of our principal components in isolation, in discrete percentages of 10, 20, and 30%. PC1 and PC2, workforce mobility and aging urban density respectively, showed the most variation, a total of 70% of the total variation in our model. However, this is more than manageable, as this is expected considering its high impact. PC3 and PC4 showed significantly less variation, and their influence is more stable. Overall, our PCs remain robust, even in the face of short-term dominance from particular socioeconomic areas. We then made a new addition to our initial sensitivity analysis that included Gaussian perturbation. Essentially, we added a random Gaussian noise to 22 input variables by 10% of their original standard deviation. This was done in order to then find the loading factors and see the structural interpretability of the PCs remained robust. As shown, they fairly did. PC1 and PC2 showed little variation and not much vulnerability to our Gaussian perturbation, meaning it's significantly robust. PC3 and PC4 did show significantly more variation. However, this is more than manageable as their influence on the ultimate vulnerability scores are fairly minimal compared to PC1 and PC2. Overall, each of our PCs remain robust, showing that policymakers can practically implement this and our results can be replicated in future studies.
So what can policymakers do with these vulnerability scores? Well, we propose a 3-pronged strategy. In areas with vulnerability scores of 70 to 100, we can look towards direct intervention strategies. One example would be grid hardening, which prepares the power grid for inclement weather events and has been shown by FERC to boost GDP by 2.5 million for every 1 million spent. We would also look towards cooling infrastructure in these most vulnerable areas. In areas with vulnerability scores of 30 to 70, we would instead look towards time of use pricing, which varies rates throughout the day based on demand and has been shown in California to lower electric load by 11.1%. In the least vulnerable areas with scores in the range of 0 to 30, we would rather look to passive strategies, such as public awareness campaigns around responsible use of power to mitigate the effects of climate change. With this multifaceted approach, Memphis policymakers can ensure an equitable and just action plan for their communities.
To conclude, we began by developing our adaptive Newtonian model to model the increase of heat temperature inside homes compared to the outdoor ambient temperature during a heat wave period. We found that apartments are significantly more susceptible to heat waves, with temperatures reaching 42.1 degrees Celsius. This should prompt policymakers to make sure insulation is not only cost-effective, but it also can withstand even the worst of temperatures to make sure families have healthy living conditions. Second, we used Surima XG Boost to model the peak demand of electric grids over the next 20 years. We found an average temperature over the next 20 years in Memphis of 38.9 degrees Celsius. This is a whopping 1.5 degree increase over the past 20 years. This should prompt policymakers to scale infrastructure alongside working with electricity companies to make sure demand can be met. Finally, we used our PCA model to map the places of highest risk in the Memphis area. We found the most susceptible and at-risk areas to be in West Memphis in comparison to a least at-risk place in East Memphis. This should show that policymakers should implement a tiered response in terms of allocating resources equitably.
There's a lot of future work that could be done, both in terms of research and policy. In question 1, we could look towards creating a vertical temperature gradient to show the effect of heat waves on multi-story buildings and towards improving insulation and roofing standards in Memphis and in the surrounding areas. In question 2, we look towards creating a Monte Carlo simulation to stress test our model and creating an electricity price fluctuation model that will show the effect on ratepayers of our current model. In question 3, we would look to directly integrate meteorological variables, which are currently only implicitly integrated through other variables, and we would cross-benchmark our model with ensemble learning methods to ensure its efficacy. Thank you for your time, and we are now ready for questions.
I can start with one. Or you want to go? So I thought the principal component analysis was interesting. You ended up with very interpretable principal components, which isn't always the case. It'd be like a cool example from my machine learning course. But I want to better understand what the value of the principal component analysis was. At the end of the day, as I understand it, you hand assigned like a plus minus one score to each of the, like, to, depending on your, that got multiplied by your weight in each individual principal component. You could have in principle done that for the original features without doing a PCA. So can you explain to me, like, what is PCA adding to the model?
Yeah, so PCA's point is to have a dimensionality reduction. So we started off with 22 socioeconomic indicators, and if you actually look at the variable names, you have a lot of similar variables. For example, we had 5 variables that were like houses aged 1970s to 1980s, houses aged 1980s to 1980s to 1990. There's a lot of multicollinearity in there. So we used PCA because of its efficacy in reducing that multicollinearity and also making it much more interpretable. If you can see our main PCs, we have 4 very clear, broader socioeconomic sectors here. And those 5 variables that I just mentioned, the age of the houses, all 5 of those variables represent the same thing. And they're all grouped in around PC2.
Yeah, that makes sense. Thank you.
I have a question on the way you address problem 2 in terms of using the SARIMA model. There's certain parameters associated with that. There's assumptions about the data. Could you comment about the parameters you chose and how you chose them, and about the data and how you tested the data?
Yeah, could you repeat that question?
So using SARIMA in question 2, how did you choose these parameters, and how did you look at the assumptions associated with the method in terms of the data?
Right, so I'll start with the assumptions. We are modeling, first, this is the explanatory variable. We are modeling heat wave temperatures. So as you can see on the screen here, there's clear 5-year patterns, even in the historical data. And we are able to find this pretty reasonable as an assumption because of real life weather patterns called El Nino and La Nina, which are cyclical. So noticing this sinusoidal pattern, we chose to use SARIMA instead of just a regular ARIMA. In terms of the parameters that you asked about, we optimized those from 1,080 combinations of hyperparameters, and we used this AIC score information criterion to reach these optimization results that you see on the board here.
We did make significant assumptions in relegating the temperature to the peak grid demand, because we didn't account for things like people moving in and out of the city, or industry, some economic details that would boost electric grid demand without being directly related to the temperature. We did assume that temperature relates to higher AC usage, the main demand on the.
Okay, and when you say you optimize them, what does that mean?
So basically, when we tested all of these combinations and we tested each of the AIC scores, and we picked the lowest one, whichever hyperparameters that corresponded with the lowest one.
Measure of?
It is the measure of how, essentially, I believe, how similar or how each of these PD and Q and capital PD and Q, how well they are a match of the data.
Okay.
And
thanks.
lower the score, the better.
Okay.
Do you use any software to do this analysis to determine PD and Q?
Can you repeat that?
Did you use any software to find those P, D, and Q?
Yeah, so we used simple Python. This is really just a for loop. Because PD and Q, so PDQ, PDQ, that's six different parameters plus the S, so that's 7. And we have a couple of combinations of each within their respective realistic ranges, and that's just a for loop.
Did you look at the assumptions, how valid your SARIMA model is? Like, did you check the assumptions?
So which assumptions would you like to?
What the data, residual analysis, autocorrelation function, anything like that? That's okay if you didn't.
We estimated a 70% confidence interval for our SARIMA results for the peak grid demand, because there are some variables I discussed earlier, like people moving in and out of the city, things outside of temperature, essentially, that we didn't account for, because that would make the model incredibly complex and wouldn't be realistic for the time frame we were given. These are some additions we can make to our model to increase that 70% confidence interval to something significantly higher.
Okay.
Mainly, our model was focused on the fact that there's these 5-year cycles that we want with Surima rather than just.
Sure, yeah. Thank you.
Any other questions? Okay, with that, let's thank the team. So Zionsville, if you guys want to say a few words of thanks, now's the time.
Yeah. Today, we would like to thank SIAM and the organizers of M3 for providing us this opportunity to compete and to present our solutions. We would also like to thank Jane Street for hosting us and our judges for reviewing our solutions vigorously. We would also like to express our gratitude to all the people that have supported us throughout our journey, including our coach, Dwight Moser, and our families, and our school principal, Karen McDaniel. Over the course of this challenge, I think we really grew as problem solvers and critical thinkers. We were able to create working solutions, even with a small team of 3 under just 14 hours, which I believe was a very big learning experience for us. In our hometown of Indiana, this topic of heat waves and outages isn't really relevant to our daily life, so we'd like to appreciate M3 for bringing in this new and diverse experience for us. We're excited to meet with everybody here and learn from your solutions as well. Thank you.